for the last session of Herb. It's my pleasure to introduce George, who's going to tell us about how to solve all of our compiler verification words.
Oh, yeah.
Take it away.
Hi, so this is joint work with Untitled from Seoul National University and Oliver Kaiser, Derek Breyer, and Victor Matveadis from MPI for Software Systems in Germany. The context here is compiler correctness. And as you know, compilers are very complex systems and they have bugs. And these bugs may cause the compiler to generate incorrect code. And that is particularly bad if you spend a lot of effort before verifying your source code that you're translating. Right? So actually there was a paper this year that discovered about 150 bugs in the mainstream compilers. And about 100 of them were of the nature that incorrect code was being generated. So fortunately, there are some people who are doing research in compiler verification. And the goal here is to provide a formal guarantee of semantics preservation. You're probably familiar with the ComCert project, which is a very prominent success story in this research area. So the question is, what exactly is semantics preservation? And the typical statement that includes ComCert says something like, if you have a whole source program PS, you compile it to a target program PT, then PT refines the source program PS. Refinement here means something like any behavior of PT, think of execution trace, is a behavior of PS. The point here is this talks about whole programs only, and it doesn't tell you anything about doing separate compilation. And that's fine for certain applications, but in practice, oftentimes the programs you run are programs that have been composed together from different separately compiled modules. And so we are interested in finding a notion of semantics preservation that is modular, in the sense that it's defined on the level of modules, compilation units, not on whole programs. And moreover, this notion of semantics preservation should also be preserved under linking. So if you look at this picture here, we have three source modules that are compiled into 3 target modules. And if each of these compilations gives us a refinement, then we want to be able to conclude, then linking together the target modules, we get again a refinement of the linking of the source modules. So in addition to this modularity, we want semantics preservation to be flexible. Flexible here, think about these source modules being compiled by actually different compilers, or perhaps even optimized by hand. And these transformations here, they may be very different in nature. They have maybe different intermediate languages and so on. And what we want is that as long as we can prove that this compiler satisfies the refinement, and this compiler, and also manually prove this transformation as being a valid refinement, then we want again to be able to conclude that linking the target modules gives us a refinement of linking the source modules. So for this, it's very important that the notion of semantics preservation does not bake in any particular compiler or intermediate languages. Finally, we want this semantics preservation to be transitive, or transitive decomposable. And here I mean that in order to verify such a compiler, it should be sufficient to verify each pass individually, and then from those separate proofs, somehow put them together and get the correctness proof for the whole compiler. Because otherwise, it's just not feasible to prove a complex compiler correct. So of course, these are all very nice things that one wants to have, and we are not the first people who are interested in this kind of thing. So let me very briefly talk about related work. You're probably familiar with the notion of contextual refinement or contextual equivalence, where the idea is that you consider the behavior of modules by first putting them into the same closing context. Right? And that's a very nice and modular notion, but it's inherently limited to a single language setting because of the same context being used. So it does not apply to the compiler verification. There's work on, or has been work on, applying logical relations to the problem of compositional compiler verification by Benton and Her, and later Her and Dreyer. And these logical relations are very powerful and modular, but the issue with this approach is a very technical issue that has to do with transitivity, as a result of which essentially the approach is limited to single pass compilers. Okay. There's very recent work in a group, Princeton and a group on developing a compositional version of ComSert, and that looks very promising, but it's also seems to be very specific to the C, or to the ComSert C language, and in particular it makes the assumption that all languages share the same memory model. So it's not clear how to scale this to different kind of languages. 2 years ago, at Popple we had a paper proposing a new method that we now call parametric simulations or parametric Bayes simulations. And they are very much inspired by normal form Bayes simulations, if you're familiar with those. They avoid the limitations of the work that I just mentioned. And therefore, we argued at that time, they have the potential to scale to this compiler verification area. However, in that paper, we actually only applied them in the single language setting to reason about program equivalence. Because that was already quite complicated. So now, 2 years later, we can we can deliver on our promise that actually, yes, it's possible to scale these parametric simulations to the compiler verification. And our current work, we call it parametric interlanguage reasoning simulations, so short PILs. They generalize these parametric simulations. It's actually fairly straightforward at a high level, this generalization. They yield the notion of semantics preservation that I discussed before. And we demonstrated that by using it to verify a compiler called Pilsner, which is programmed in Coq and verified in Coq, and is not particularly complicated, but it's also not trivial. I will say a little bit more about it in a moment. We also used it to verify an interesting, challenging example from the literature, which is a one-line ML program on one side, basically, and a quite complicated assembly program on the other side, which implements the ML program, but in a very obfuscated way, first decoding its own instructions and replacing its own code and memory and so on. And thanks to the flexibility of this approach, we are then able to actually link this refinement, or this assembly module with other modules produced by the Pilsner compiler. So in the remainder of the talk, let me first give you a very brief review of the old paper, basically the key idea, basically, of parametric simulations, and then tell you a little bit more about these parametric interlanguage simulations, including the key results. In these parametric simulations, the central question concerns functions. So think about when you want to consider functions as being similar. Naturally, you want to say something like, okay, you have these two lambdas here, and you want to plug in some value v1 into the first one, and a value v2 into the second one, and then you want to say these are, again, similar computations. And the issue is, what should be the assumption of what the values v1 and v2, the arguments. In applicative simulations, the idea is you simply require them to be syntactically equal. So it's actually the same argument on both sides. Okay? And that works for simple languages, first-order languages, and very simple higher-order languages, but it's known not to scale to richer languages in the sense of being unsound. So the interesting question is really, what is if those things are actually themselves functions, those arguments, with the higher order case. And the answer in parametric simulations is that, well, let's assume they come from some relation u. And what is u? Well, u is unknown. The idea is to parameterize the whole similarity relation by this unknown relation u, and then define the ultimate similarity by intersecting over all possible relations. That's very roughly the idea. Now you may wonder, how can this work if we don't know, if these arguments, they come from you and we don't know anything about you, that means we don't know anything about your values. So how can we possibly show this similarity? And to account for this, parametric simulations extend the usual conditions of similarity with an additional case. So usually you have a condition talking about termination case, so if one side terminates, the other side will terminate. If one side takes a step, the other side can take a number of steps, and then you have again similar computations, right? And now in parametric simulations, there's an additional case which says that if your first program is a function call, and your second program steps to a function call, and you can show that the functions are actually such external unknown functions coming from you, then in that case, so intuitively now they pass control to the context, and you can't continue because you don't know what they are doing. Right? So then at that point, it's enough to show that your arguments here are similar, and assuming you get back similar results, you are again recursively similar. But that's very roughly the key idea, and maybe an analogy may help you to understand better. So if you're familiar with logic relations, then parametricity, you know that the client of ADT or polymorphic function behaves parametrically in what the actual types are that receives as arguments. Right? And even further at the relational interpretations of those types. And here you can think of as the proofs of a refinement of a similarity being parametric in the relational interpretation of the function type. And the benefit of not knowing anything about your external functions, and this is a very intuitive statement, is that it constrains your proof, and this constraining makes them easier to compose. So in the proof of transitivity, for instance, it's these unknown relations. The fact that we can choose this unknown relation, we are exploiting very much. Now let me come to hills. So as I mentioned, they generalize the parametric simulations to this interlanguage setting where we have a different source and target intermediate language. Right? And it's also, as I said, at some level it's very straightforward, but there are many, many technical details that make it tricky. And in this talk here, I can't really go into these technical details. So instead, I will try to give you an overview of how this thing works, or what it looks like, and state the key results. Because the nice thing about this is that the key results are very, very simple to understand. So the compiler that I mentioned before, Pilsner, is compiled from a source language S to a target language T, going through some intermediate language I. Okay? And S is, you can think of as ML. It has higher order state. It has I/O primitives. It has universal types, existential types, recursive types, and so on. The intermediate language is a CPS-based language, based on the source language, and it's completely untyped. Okay? It's inspired by Andrew Kennedy's CPS language. The target language is a machine language. It has some standard instructions for memory access, load store, jumps, conditional with branches, and so on. It has a fixed set of registers. It has different addressing modes for operating on stack, register, or heap. But we are assuming, for instance, infinite memory. Okay. And the structure of the compiler is as follows. So we start in the source language, doing CPS conversion into the intermediate language. There's some function inlining going on, and there's a that code and that variable elimination where we basically if you have a let binding where you don't use the variable, you replace it by the body. We have hoisting where we lift let bindings out of function and continuation definitions, and we commute let bindings in order to enable this class here, which we call it deduplication. So if you have a consecutive let bindings of the same expression, we merge it into a single one. That's a kind of a common sub-expression elimination. And then finally, there's a code generation which produces the machine code. Maybe two things to mention. The CPS transformation establishes a uniqueness property of bound variables. So each variable is bound at most once. That makes it simpler to implement these transformations here. And it also makes sure that the continuations which you have in intermediate language, that they are used only in a linear fashion. And these properties are preserved by all the transformations. And crucially, the code generation relies on this linearity property. So it allocates continuations on a stack and set up on the heap. And so once a continuation is used, it will be popped from the stack and forgotten about, because linearity ensures that it will never be used again. Yeah, thanks to Neil for a discussion a long time ago. Maybe he doesn't remember. Right, so now let's think about the correctness statement. Says Pilsner applied to some module. If it gives you an output module M prime in the target language, then that refines the source module. And here this refinement relation, T for target, S for source, is what Pils gives you. Right? It's defined in terms of Pils. And as I mentioned, the way we want to prove this is by having a proof of each pass. Right? So we're actually going to prove that CPS is correct, that inlining is correct, and so on for each of the passes. And what that actually means is that in total, we need 4 of these relations, not just the one I mentioned here between target and source, but also one between intermediate source, and so on. And the way this works in Pils is that we actually have a single generic definition of this model, of this refinement, which is parameterized over language A, the output language, and language B, the input language, that both implement the same abstract interface. So the interface requires an abstract set of values, an abstract set of continuations, notion of module, and some operations on using the module, and a notion of configurations, machine configurations, which have a transition system. Right? So it's actually a very simple and abstract. Moreover, this definition is parameterized over a global word for these 2 languages, which I will say more about in a moment. And to be precise, actually we have 2 versions of this definition. So there's a type version and an untyped version. And the nice thing is that the untyped version is obtained simply by erasing all the types. So it's still fair to say it's a single definition. Now these refinements that I mentioned on the previous slide, they are just concrete instances of this generic definition. And for the refinements involving the source language, which is the only typed language, we use the type version of the refinement of the model. And for the other 2, the untyped version.
I have a quick question.
Yes.
So this PS target source relation, is it just the composition of the three? Okay.
But I will get back to that too. So let me briefly talk about these words. So in general, words are abstractions of a program state. They let you attach relational invariants to pieces of the heap or stack in your programs, which will be useful or essential in doing your cruise. In Pils, a word is composed of a local word and a global word. And the local word is proof specific. That means when you do your proof of refinement, complete refinement, you get to pick that word. And usually you use it to talk about local state. Now in the Pils compiler, in the Pilsner compiler, the transformations on local state are not very interesting. So the local word there does not play a very important role. But in the example that I mentioned with the self-modifying assembly code, it's very crucial that the local word is very flexible. And here we are based. This is based on previous work on using state transition systems as words. So actually, you can think of a word being a state transition system.
You have a blue and red here. Is that typed and untyped, or is it just
No,
blue
no,
and
sorry,
red?
that's just to highlight the words.
Okay.
Right. The global word is, well, it talks about global word, the global state, such as references that are passed around at reference type. Right? And it's, in contrast to the local word, it's model specific. So meaning each of these four refinement relations has a particular fixed global word. And each proof using that refinement relation uses that same global word. Here in particular, in pills, they describe things like how values are being used, so the calling convention for functions and the representation of other things. For instance, you may ask the global word, what is a pair, or how are pairs represented? So there's a component in the global word called a value query handler, which you give the current state of the word, and you give it two values, and you get a set back of those values which are in this particular state considered pairs of v1 and v2. And in the source language, for instance, that's very simple. You just look at the value and you know it syntactically. But in the target language, you actually have to look into the state, which contains some database of what the current values are, and there must be an entry saying, okay, at the moment, in this state, v is a pair of v1 and v2. And then the global word for the assembly language has to make sure that this set only ever grows over time. So once a value is a pair of v1 and v2, it's always going to be a pair of v1 and v2. And that's important because it reflects that in the source language, values are immutable. Similarly, you may ask, when does a configuration, which is the thing that steps, right, that executes, when is a configuration a function point? Right, yet v1 is the function, v2 the argument, and k is the continuation which is being executed. In the source language, again, that's very much what we expected to be syntactically. It's not shown here. But in target language, it's more complicated. So again, we look into the state, make sure that v1 is currently a function with code pointer n. The program counter must be exactly this n, right? And in addition, the function itself and the argument in continuation must be in corresponding registers. So for instance, k must be in the return register. Okay. Now let me come to the results, which I mentioned are very simple to state. There's this transitivity or transitive composability, which is two parts. So these are refinements here, a refinement between target and intermediate with source. These are contexts talking about the functions that are being imported and the functions that are being exported by the modules with type annotations. Here in the untyped model, type annotations are erased. That's the notation. And it simply says if we have a refinement between ti and between is, then we have one between ts. Okay. A similar property for the composition of the ii refinement and the is refinement. And these are very hard to prove, but the proof pretty much follows the transitivity proof for the original parametric simulations in the Popple paper. And the nice thing is that because of our generic formulations, they're actually very similar. Now, once we have those two, we can basically do an induction here to repeat, to get a reflexive transitive closure here, and then plug it into the first one, and we get out this one. And this is exactly what we need to verify pills now. So this one here will be the code generation, this will be the CPS transformation, and those will be the intermediate optimizations. And then using this rule, we can plug those proofs together and get the proof for the final compiler. Okay, quickly, the traditional correctness result is adequacy. It talks about whole programs, right? So if you have your two modules which don't have any imports, and they have a main function, then the behavior of the target module refines the behavior of the source module. But in addition, in pills, we have a modularity rule which talks about linking. So this is exactly what we had from the picture in the beginning. If you imagine you have a refinement here and a refinement here, you link them together. So this is what this talks about. Here you can see that this module may use exports from the first one. Right, and please note that none of these properties here talks about a particular compiler, and even none of them talk about a particular intermediate language. So, as I mentioned, we can use this to link compiler-produced code with hand-translated code, and still get a refinement result.
Could you go back to that next slide? So you have a O+. Is that like some linking protocol?
That's just the notation for linking. Yeah. So we assume there's a linking defined at the source language.
But you have a plus at the T as well.
Yeah, sure. For the type, of course, we have linking at the time between assembly modules. Yeah. It's a different plus. Yeah. So let me conclude briefly. We showed that what we claimed earlier actually works. We demonstrated that the generalized parametric simulations give us the kind of semantic preservation that we're interested in. And we have tons of ideas for future work. Thank you very much.
Questions?
Yes.
Thank you.
Could you go back to the last slide on
Go ahead.
transitivity?
Yeah.
Yeah, here I would naively expect that you could prove something like the rule that there for any languages ABC abstractly without knowing what these languages are.
Yeah.
So is it false in general?
I'm pretty sure that currently it's false. The point is that I think it's possible to do this in general, but then you need to axiommatize a lot more about your languages.
Okay.
Particularly about the global words that are being used.
So can you go back to the definition of parametric simulation? So I didn't understand where you use this
The review part?
U.
So yeah, this review here was very rough. It's very simplified. What is the
So
question?
here you use it basically on the arguments of the function, but later you say you use it also for functions when are two functions related in U.
So in general, it's used basically everywhere. So there's this unknown relation U which contains only functions, okay? And then there's a closure operation which lifts that relation to any arbitrary type. So for instance, for pairs it says that recursively the components are related. And then for instance, when your programs terminate, you need to show that the values are in this lifted version of the unknown relation. Also here, which I didn't really mention explicitly, but the arguments you also assume, the result values, you also assume to be related by the closure of this U. Similarly, here the arguments that you pass to the functions have to be related types. Okay, we may be confused because I'm omitting a very important detail, which is that in parametric simulations there is an assumption that this unknown relation actually contains essentially your current co-inductive assumption. So in your proof you're constructing a simulation relation, right? And roughly the assumption is that U always at the very least contains your own simulation relation. So the way
so
you need to show
you increase, you add something to U or on the way. You do fixed points or?
No, you don't. We add some. So the point is that at those places where you need to show that something is in U or in the lifting of U, sometimes the way you show that is by showing that it's in the actual simulation that you are constructing at the moment. Okay. That's for the things that you are proving yourself being related. For the things that actually are unknown, because you already know that they are in there.
I guess I look at it.
I think the answer is that U contains, you assume that U contains all the sort of similar terms, or similar functions. It may also contain other things, but it at least contains the similar functions.
Ah, okay. So it's a congruence, something like
U is not a congruence.
Yeah, you would not be
that. It's
a congruence.
compatible.
It has to at least contain the good stuff. It can also contain bad stuff.
Go ahead.
Okay, so the source language in pills is very, very rich. It's got recursive types and references and things like that. How much simpler would things get if you like took out some of that stuff? Like say I want to implement a kernel type checker for dependent types or something like that, where you don't have like general recursion. Like how much of the complexity is coming from references and recursion?
References make a big difference. The recursion, I mean, here it's just parametric simulations already were designed for dealing with recursion, right? So, yeah, I don't know if you remove recursion, then I'm not sure if you still need to use parametric simulations. Yeah, sure. I mean, something would be similar, but references make a big difference.
But it's worth noting that also, I mean, references and recursion also limit the kind of optimization, or kind of program transformations you can make. So there's always a trade-off.
Let's thank the speaker again. Yeah, for our next talk, Philip telling us about how he's done some really difficult mathematics and packaged it up very nicely in Cox so we can all use it without having to be nearly as clever as him or Lars. So,
well, mostly Lars. It's based on like the math is all based on earlier work. So I just needed to type it up. Basically. So yeah, I want to talk a little bit about the project that we did mostly the past year. This nice library for reasoning about higher order imperative programming languages. Now, I would like to convince you why it's nice. And well, the point is that reasoning about these kind of languages is generally difficult. It's kind of like what Philippa said earlier today, that especially if you want to build very higher order models, that you don't really want to think about it, and especially if you're thinking about very difficult languages like JavaScript, for instance, right? You really don't want to be bothered with whether your models are even well defined. Right? So there has been a number of techniques developed in recent years in order to help building these kinds of models. But still, as long as you don't have a resident expert in your group, you probably don't want to make sure that everything checks all the boxes, because, well, you have better stuff, you have new stuff to do. And also, this very much limits the newcomers to the field. So if you don't know this stuff already, then it really takes a lot of time to dig through the papers. So why do we think a Coq library is a good idea? Well, I think it can address two main issues. So for the first thing is, well, just research-based, research-directed. So first, it can increase the confidence in these complex models because, well, if there's only so many people who can actually read through your model, well, it's even some of the reviewers who are very well knowledgeable in some of the other aspects of your work might not be perfectly fine with you using all sorts of complex math to define your things, right? So verifying your logic or your logical relation can definitely help increase the confidence. And also, it can definitely help guide the development of new models, especially for people who don't necessarily have a resident expert on hand. The other reason why we developed it is for teaching. So, especially for if we have graduate level students who are getting into this area, well, like I've mentioned, it is very steep learning curve. So especially for some people, this kind of tool that they could play with could definitely alleviate the kind of well, this learning curve. Yes. Oh, this has gone wrong. Well, so what kind? What should the? What, okay, so what a library like that? What properties should it have? Right? Three main ones, I would say. It should be powerful in order to be useful in the cutting-edge research. It should be readable in the sense of understandable. It should help guide this development instead of the user having to jump through all sorts of hoops in order to define their model, right? So it definitely should be as low on boilerplate as it is possible. And, well, teachability for getting new users to be able to understand the kind of theory we're building. And, well, I would like to say briefly why I think our library does that, and then show you a little bit example. So, as for power, we have built two, except for basic examples, we have built two more interesting projects. So one is a cutting-edge logic for a high-order separation logic for that is actually currently submitted to a conference, and it has been fully verified using this library, so built on top of the library. And we have also had a research intern in Aarhus recently who was working on formalizing our earlier work on a logical relation for high-order concurrent programming language. So these are really two related models that require very much, as powerful an approach as possible, really, these days. Now, as for readability, the setup is built in a way that makes most of the usual notations work directly in the kind of types that we will be using here, which makes the code much more readable. So there have been earlier attempts, and well, at least I have had a lot of time trying to dig through them and understand what was happening. And the as for the third thing, we have written an early draft for now, but we are working on a tutorial that would allow, hopefully, graduate students to start learning this stuff and understand how these models are built. And we are expecting to try it out on a couple of master's students this semester. And also, the collaborators we've had for both of these bigger projects, they have managed to pick up the library, the design of the library quite fast. So I think this works also as a good indicator that both readability and teachability should work nicely. So in the remainder of the talk, I would like to work through a simple example, well, a little bit of working through, not in all detail, of a lambda calculus with higher order references. This is the first example, so we will show a little bit of how we can define an interpretation of types in a sort of simple unary logical relation. So higher order references, well, what is the problem in the first place? The problem is interpreting the reference type. So if we try to assume that the type of the interpretation function should just be predicates over values, right? Then the question arises, well, how should we define the interpretation of the reference type? And the problem is, well, usually we want to put some locations there, but which locations are good, which locations are not good, we don't know, right? So we need a description of a good heap, of good locations. This is usually called a world, and the problem is that if we have general references, if we have higher order references, then this world has to also describe not only what locations are defined, but also what type the location has, right? So, well, and obviously if we have a world like that, we also need to to change the definition of T, it can't just be predicates over values, they have to also depend on the world, right? So, well, let's take something along these lines, right? Worlds and a monotone map, monotonicity, to ensure that we can allocate extra stuff into predicates of values. Now, the problem here is that if we substitute the definition of worlds here, T occurs in a negative position, and so this equation would not, in general, be solvable, would not define, in general, a good type. So, well, this is the general problem that this library tries to solve. There's a lot of stuff built around the problem, but the core of the library is a solution to this kind of recursive domain equations. So how do we do that? Well, we have an equation like this, and well, and in general we can't solve this. We know. So instead of solving for just any old type, we will restrict ourselves to types with more structure. So we'll use a subclass of metric spaces that's called CBOld, or recently coffee, that is suited to describe approximation. Now, if I were listening to talk about Coq and someone told me that they are going to use metric spaces, I would be rather scared, because, well, the last thing you want to do when you're using a theorem prover, an intuitionistic one to boot, is to reason about real numbers. Now, luckily, this subclass has nothing to do with real numbers, so you should be calm. There is no real numbers involved, because this one, this subspace is generally speaking a type with a notion of equality up to n steps. So you can think of those as very general notion of step-indexed types. Right? We can compare types only up to n steps, where n is a natural number. And we'll also need a notion of non-expansive maps, which are functions between those spaces, such that they map n equal arguments to n equal results. And this is reasonably simple. This only has natural numbers, and kind of has this reasonably familiar feel, I hope. And what's more important, we can easily encode it. And now, if we restrict ourselves to this space, to CBOld, there are actually solutions of certain forms of the kind of recursive domain equations we have. Now, I won't go through any of how these solutions are constructed. This is not the point, right? This is not why we're building the library. We're building the library so that no one needs to care how it's done. What we need to care about is how the interface looks like. So for the interface, we need to provide several things. The first one is a map that will describe our recursive domain equation. So what is T on the left there mapped into, right? So we had this equation T, and T was mapped into the right-hand side here. So, yeah. So in our case, we'll take the T, and we'll map it like so. There are two changes here compared to the previous slide. There's an n here in addition to m. This means the non-expansive map, like I described a while earlier. And the predicates over values have changed into uniform predicates over values. So this is the space of step-indexed propositions, step-indexed predicates over values, which is also provided by the library. And this is all well and good, but we also need to show that any of these non-expansive maps between two types can be mapped into into the results of this FO here. So that should be FO here in both places. And what's more, contrariantly, because we're solving for a negative occurrence. Right? So what can we do? As usual in these kinds of things, there is only one thing we can reasonably do, and well, this is the thing. So we take a function from S to T, we take a uniform predicate, we take a uniform predicate, this one, f of t, FO of t, and we take a world, which is the first thing here. Right? These were all function spaces until now. And we look at P, and now P expects something it's f of s, so it expects some world with an s instead of a t. So we map the function we were given over the world. Never mind. There's just one thing you can do there. If you compute, it will come. There is a thing here though that I haven't written. So here the map is supposed to be non-expansive, and here the map is supposed to be non-expansive. So what the library will require of you here is a couple of proofs. But this is the way you'd have to do it on paper too if you were to write out all the details. But right now you can't omit those because the library will just not let you. So there are a couple of extra propositional things that we need to show. We need to show that FO and FA together are functorial, so preserve compositions of arrows, non-expansive arrows, and identity. And we have to show that F of a unit type is inhabited. These are side conditions that are required by the construction, and none of these is generally hard. So, yeah. So this is a short description of what has changed here. Yes, we have uniform predicates, step indexed. We have non-expansive maps, which preserve the step indexedness, and we have several additional proofs. This is all. This is all we need to provide in order to solve a recursive domain equations. Now what we can do, so yeah, as you can see, it's reasonably easy. Now what we can do is crank the handle on the construction and get a solution. A solution also has an interface, and this is it. So we have a type, a complete bounded ultrametric space, CV alt. Yeah, this is our solution. We'll use it later to interpret stuff. And we have this is the same. Sorry, pretty. So this iota here maps our solutions into whatever we have there, right? So, we've had here FO of t, these maps into uniform predicates of values, with t in the worlds, right? So, iota in our case will map our solution into worlds with pt instead of t, mapped monotonically and non-expansively into uniform predicates. There's also a map going in the other direction, and they form an isomorphism, which allows us to convert the things that we find in the worlds into the things, into our types, into FO of them, and back again. Now, the one thing that might be worrying here is these mysterious triangles. This is because we can't solve exactly the equation that we've written out, but we can nudge it a little bit and solve it after a little change here. Now, what this means, this triangle, is that if T1 and T2 are n plus 1 equal, then after we convert them with iota, they are n equal, only n equal, right? So this is also related to some stuff to later operator in the topos of trees, which is another of these very fancy models. But in general, it just means that you only get n equality if you start with n plus 1 equality. So basically, especially if you're doing this work in the theorem prover, it only means that sometimes you will get things at one step lower. So okay, so now how can we interpret reference types using this? Well, we are supposed to go into FO of t, right? So our types of worlds, monotonically and non-expansively mapped into uniform predicates of values. So okay, so we take a world, we take a step index and a location, and the definition is that L is supposed to be in the domain of world. It's supposed to be defined like the world is supposed to be. It's what the world is supposed to mean. And whatever we find in the world, if we map it back into the space, into this space, is n equal with this index n to the interpretation of type t. So, in a sense, this ties the interpretation of t to the type that we find in the world. So this is again reasonably simple. There's nothing very fancy going on here. Now the other thing we usually have to do if we have the kind of worlds here is we have to say when is a heap well defined, right? So this is also step indexed and also reasonably simple. So a proposition that says that H has type W in at step index n means that all the locations in the world are in the heap. And
should it be L?
Yeah, it should be L.
Okay.
And the value found at HL is in the type that's indicated in the world, right? So we look up the type in the world, map it through the iota, and apply the world again, because the image of